Okay, so not only do you have to know the products of the reactions, that's step one. And we've also talked about the regioselectivity of a reaction, where the thing that you're adding gets added to when there's a choice, when one side of the double bond is different than the other side. Then the other consideration that you need to make is stereospecificity. And there are some reactions that are stereospecific. And here's an example of three of them. And the reason I bring up these three is that they're all explained by a similar intermediate. Now, I'm going to start with the same starting material, and I'm going to add something across the double bond. And so all of the products are going to have a structure that looks like this. And so I'm going to just go ahead and copy that over. And they're all going to involve a very similar intermediate. And the intermediate is going to look like this. It's going to have the CH3 and the H still pointed in that same direction. I put it on its side. And it's going to involve the CH3 here pointing up. And then it's going to involve some sort of cyclic structure. And we'll fill in the cyclic structure here in just a second. Okay, well, let's go ahead and do that now. So for the addition of Br2, we form a bromonium ion. For the addition of for this peroxy acid reaction, we're going to form a protonated epoxide. We're going to ultimately, it's going to be a diol formation. And for oxymercuration, demercuration, we're going to form this other interesting cation, this mercury-based cation. So they're all ring structures. They're all three-membered rings. And the point of this question is to show you, the reader, that in each of these situations, there's going to be a stereoselective outcome. Now, it's going to be a little bit harder to see with oxymercuration, demercuration. I'll show you in a second. But for the next bromine to add in this reaction, it has to add on the opposite side of the ring. Now, we could show it actually adding over here, and this one moving out over to there, which is going to push that CH3 down, and that's what's harder to see because it's hard to draw that arrow going the correct direction, kind of going behind it, moving that CH3 down. And so what are we going to end up with here? We're going to end up with CH3 going down and the bromine coming up, but that means that this bromine had to go in the opposite direction. And that's what we mean by stereo-specific. This is a anti-addition. You can never get the two bromines to add in the same direction. And so the same thing is happening with the addition of with the diol formation. I'm going to get ultimately I'm going to get an addition of an alcohol. It has to go the opposite direction as the cyclic intermediate, and so the two OH groups are going to be anti to each other. There's nothing we can ever do about that. Now, it's a little bit harder to see with oxymercuration, demercuration, because we're not actually forming a stereocenter generally. So I can still show you the CH3 sort of moving down. And I'm going to form an alcohol. Actually, if this is forming an ether here, since my nucleophile is going to be methanol. But at the end of the day, what I have here is H and H. Now, I can show you this if I replace this with a deuterium. So if I replaced it with the deuterium, then I have a deuterium here. Instead of having a hydrogen, I have a D. So we would see that ultimately I'm going to have the hydrogen pointing down and the D pointing up. And so we would end up with a situation where the CH3 and the OH and the deuterium point in the opposite directions. So it's harder to see with that one, but it's still anti-addition at the end of the day. There's still, of course, the possibility of having the other stereoisomer. And so we can say enantiomer, enantiomer. Now, I use en to say, I don't really mean enantiomer. I just mean other possible stereo configuration. Because keep in mind that this is a stereo center as well. And so what that means is that we're not actually forming enantiomers. What's the actual stereochemical relationship between the products? They're diastereomers. And so when I use enantiomer, I'm just saying, look, it's the we want to be able to tell the reader the other stereo center forms between those possible products, and so that's what we use to signify that instead of having to draw it out. Okay,